Hello, AP Physics 1 students. Let's take a look at some of the concepts questions we didn't get to cover in class. Hopefully you've already answered these for numbers 5 and 7. Number 5, what's the range of wavelengths of visible EM radiation? Well, at this point you've said it so many times, you should definitely know this right off the top of your head. Of course, it is between 400 and 700 nanometers, right? It's just a good range to know, so you can evaluate if any of the wavelengths of light we're looking at are in our visible spectrum or not. It's also good to know which end is which, right? So we know that violet is the high frequency, and it's going to be the low wavelength, so the 400 nanometers at the violet end. Red being our lower frequencies, it's going to have the larger wavelength, so the 700 nanometer range, that's in the red end of our spectrum. So there'll be a little more interesting question, why do we only see that range of EM radiation? So if you thought about it any bit, you probably have some ideas as to the nerves in our eyes, the photoreceptors, the rods and cones you've heard about before, and your first answer might be, well, those are the only wavelengths that we can see. Okay, that's great, that's true, but the real question is, okay, why does that happen? Let's get deeper, right? Because in the electromagnetic spectrum, it's a huge range of wavelengths. 400, 700 nanometers is a ridiculously tiny, narrow band of that spectrum. So why do we only see those wavelengths and nothing else? Well, let's consider where we get most of our light from. And that, of course, would be the sun, right? So let's plot a graph, because, we love graphs. And we're going to plot a graph of the intensity of sunlight versus frequency. And we'll specifically do it for our sun, although it turns out the graph we're going to see really is a sort of generic plot for anything that glows, anything that gives off electromagnetic radiation. And so for any star, our sun included, the plot looks something like this. In the lower frequency range, it's low, and in the very high frequency range, it's high, and it peaks somewhere. Not necessarily in the middle, it's sort of an offset bell-shaped curve. And different glowing objects peak at different frequencies, depending on the temperature. Specifically, our sun peaks in yellow. Our star is a yellow star. It gives off more yellow light than anything else. Why is it significant? Well, where is yellow in our color spectrum? Yeah, it's pretty much in the middle, right? So let's think back to the beginning of life on Earth when some small-celled organisms were first evolving and they had some sort of optical receptors. They weren't eyes yet, but they had something that would take in light and process it. And so it was literally survival of the fittest. Those organisms that could see yellow, which our sun gave off more of, and the surrounding wavelengths are the ones that survived. And other organisms that could see outside of that range, well, a lot of them died off. And so the vast majority of organisms on Earth can see yellow and the surrounding wavelengths because that's how natural selection works. Everything else kind of died off. So this does, sort of beg the question, if we found life that existed on some far-off planet surrounding some sort of sun that didn't peak in yellow, what would they see? Let's say if it peaked in red, right? So they would see red and the surrounding wavelengths into our color spectrum, but then they'd also see into what we call infrared, and they would actually have names for colors that we couldn't even comprehend. They'd be describing something that we couldn't really understand. And so I guess what this all comes down to is when Kal-El first came to Earth, I imagine he had a lot of adjusting to do. Some of you will get that. Some of you will have to think about it a little bit more. Okay, let's move on to number 7. Let's take a look at these other optical phenomena, and we're going to talk about the defining property or properties of waves that explains it. So letter A, I'm sure you've all had this experience, looking at a grill at a cookout, and the air above it looks kind of shimmery. Maybe like on a hot day, the street looks kind of shimmery. What's going on here? Well, the hot surface is radiating heat, right? And that's causing the air above it to move. And so what you're doing is you're seeing light from the other side of that hot air coming through the hot air, and the air literally moves, taking the light with it. And so the light is traveling from a lower temperature into a higher temperature into a lower temperature. It's sort of changing media. And which property goes along with changing media? Well, that's refraction. This is a refraction effect. How about letter B? Stars are so far away that we really should just see them as dots of light, except that's not how we see them. If you ever look up at the sky, right, you see the light sort of spread out into points. This is why we draw like a 5-pointed star. You can even see this photograph here. You can see the light separated or spread out vertically and horizontally. So what property of waves would explain this? So you're thinking of something that would cause the light to spread out. That's the key here. And so hopefully you've identified diffraction. Right? When a wave goes through an opening, it spreads out. So the question is, where's the opening? So you may think it has something to do with our atmosphere. It's not. It's something much, much closer to you. It's actually your eyes. Every single time you rub your eyes, if you get something caught in your eye, like, eyelash or something like that, a little bit of grit, and you rub your eye, you actually cause tiny little scratches on your cornea. Not enough to really hurt you, but just causing little divots there. And so when the starlight goes through those tiny little divots, those little scrapes, I guess, on your eye, it acts as a diffraction grating and actually spreads the light out. And so it turns out the older you are, the longer you've lived, the more you've rubbed your eyes, the more you see this effect, which means it goes the other way as well. The younger you are, the less you see this effect. So being a physics teacher, and knowing this, when each of my daughters was born, when they were just a baby, I would take them in my arms outside, and I would stare up at the sky, and I'd tell them to look at the stars, and I'd say, okay, so tell me, what do you see? Strangely enough, none of them ever answered. All right, on to letter C. Why do stars appear to twinkle, right? Hence the song, Twinkle, Twinkle, Little Star, right? Starlight doesn't really twinkle. It doesn't sort of go in and out and move all around. What's causing this? This has to do with our atmosphere, right? The light, before it gets to our eyes, has to pass through this big blanket of gases called our atmosphere. And the atmosphere, the air, is just about always moving. And so the light is actually being taken with the motion of the medium. But it's going from the vacuum of space through the atmosphere into our eyes. It's changing media. This is a refraction effect. And lastly, why the surface of a CD or a DVD sort of spans the color spectrum. If you've never taken a look, because I don't know how many of you really are using CDs or DVDs much anymore, but this is a photograph of a DVD I have in school, and you see these different colors, right? Now, it's not the continuous color spectrum. Hopefully you recognize these as the same colors you saw when we held the diffraction grating up to our webcam. We looked at the fluorescent lights in my classroom, because I took this photograph in my classroom. Is the exact same separation of colors we saw with a diffraction grating, right? So what we're looking at, well, this is acting like a diffraction grating. This is diffraction, and we see constructive, destructive, constructive, destructive. It's going back and forth. This is also an interference pattern. So this is diffraction and interference.